Our second speaker is Il-Seung Jang from Seoul National University. He's going to talk about flagged Littlewood-Richardson tableaux and branching rule for orthogonal groups.
Thank you for the kind introduction. And I'd like to thank the committee members and organizing committee. Today, I will talk about the branching rule for orthogonal groups. More precisely, I explain a combinatorial formula of the branch multiplicity for orthogonal groups in terms of the Littlewood-Richardson tableaux with a flat condition. This is joint work with Jae-Hoon. My presentation has three parts. First, I will explain the Littlewood restriction formulas. Second, we will review some two formulas of the branch multiplicity for symplectic groups, which generalize Littlewood formula. In this part, I will explain motivation for our work came from an observation on these two formulas. Finally, I'll state our main result and I'll explain the main ingredients of the proof briefly. That is the subgroup of Jn preserving the non-degenerate skew-symmetric binomial form on Cn. On means the orthogonal group, which is the subgroup of Jn preserving the non-degenerate symmetric binomial form on Cn. Let us consider finite-dimensional irreducible modules over the classical groups. Let P of M be the set of partitions whose length is less than or equal to M. Then it is well known that there is an unturned correspondence between finite-dimensional irreducible Jn modules and the partition set P of M. So we denote by V sub Jn lambda a finite-dimensional irreducible Jn module parameterized by the partition lambda. Similarly, for a classical group Gn, there is an unturned correspondence between finite-dimensional irreducible Jn modules and a certain partition set depending on Gn. So we also denote by V sub Jn mu a finite-dimensional irreducible Jn module parameterized by the partition mu. In this talk, the branch multiplicity for Jn and Gn associated to the partition lambda and mu means the number of irreducible module V sub Gn mu in the restriction of V sub Jn lambda as Gn module. Since the finite-dimensional module of classical groups are completely reducible, so by Schur lemma, this branching multiplicity is also given by the dimension of a Ham space from V sub Jn mu to V sub Jn lambda. The main question in this talk is that do we have a nice combinatorial formula for the branch multiplicity? As far as I know, most classical and interesting results is the Littlewood restriction formulas. In 1944, Littlewood proved that the branch multiplicity can be described as the subsection free sum in terms of Littlewood-Richardson coefficient if the length of lambda is less than or equal to n over 2. Unfortunately, this formula does not hold in general when the length of lambda is greater than n over 2. Then the natural question is that what is a combinatorial formula for the arbitrary lambda? In this part, let us review two formulas, generalized Littlewood formula in the symplectic case. For this, we first review Littlewood-Richardson tableaux in more detail. The Littlewood-Richardson tableau, shortly LR tableau, corresponding to partition alpha, beta, gamma, is a semi-standard tableau of shape alpha or beta with context gamma, whose words is a lattice word. In this talk, we denote by LR alpha, beta, gamma the set of LR tableaus corresponding to the given partitions. Then the error coefficients means the number of error tableaux. Let me give a simple example. Consider this Q tableau T. Then the shape of T is obtained from the partition 5, 4, 3, 2 by removing the partition 3, 3, 1. So this partition has shape alpha or beta. Also the number of letter ones is 5 and the number of letter twos in T is 2. So this Q tableau has content 5 and 2. Also, the word of T is given by 1, 1, 2, 1, 1, 2, 1. Then this word is lattice word. That is, when we read this word from left, then the number of letter I is always greater than equal to the number of letter I plus 1. So this tableau is error tableau corresponding to the partitions alpha, beta, and gamma. Here, let me review another notion which is equivalent to error tableaux, so-called companion tableaux. These tableaux play an important role in our work. In this talk, we may identify error tableau T with its companion tableau S, which is determined by the letter I is in the J's law of S, if and only if the letter J is in the I's law of T. For example, consider the error tableau T, then the letter 1 appears first, third, and fourth row of T. So the first row of S is 1, 1, 3, 3, 4. Then by the same way, the second row of S is given by 2 and 4. Let me introduce the results by Sundaram. For this, we need to consider certain error tableaux with some condition. Let error till alpha beta gamma be the set of error tableaux satisfying each other letter 2i plus 1 appears no lower than the n over 2 plus i's law. For example, under this setting, we consider this error tableau. Then the other letters 1 and 3 appears no lower than third and fourth row of this tableau. So this tableau satisfies this condition. Let us consider the corresponding condition on companions. By identifying error tableaux with its companions, we regard this error till alpha beta gamma as the set of companions satisfying the rightmost entry in the 2i plus 1's row is always less than or equal to n over 2 plus i. For example, consider the error tableau in the previous example. Then the corresponding companion tableau is given like this. Then in the first and third row, the rightmost entry sigma 1 and sigma 3 are given by 1 and 4 respectively. Then these entries satisfy this condition. That is, sigma 1 is less than or equal to n over 2 plus 0, and sigma 3 is less than or equal to n over 2 plus 1. Now I introduce the Sundaram's combinatorial formula of branch multiplicity for Jn and SPn. Let C till alpha beta gamma be the number of Sundaram's error tableaux. Then in 1986, Sundaram's proved that for arbitrary lambda and mu, the branch multiplicity can be described as a subsection-free sum in terms of Sundaram's error tableaux. This tableau recovers Littlewood's formula. In other words, when the length of lambda is less than or equal to n over 2, then the condition on this set is vanished. That is, in this case, this coefficient equal to the usual error coefficient. So in this sense, this formula recovers Littlewood formula. Next, we consider another formula for the of the branch multiplicity for Jn and SPN. Recently, Lecouvey-Lenart obtained another branch multiplicity formula for Jn and SPN in terms of the companions of error tableaux associated to the conjugate partitions. Then, by using this bijection, the formula can be described in terms of companion tableaux for these error tableaux. I will explain what it is later. Anyway, under this description, the formula has a similar flag condition as in Sundaram's formula. In fact, indeed, this is the reason why we prefer to use these error tableaux. Let error alpha, beta, gamma, pi be the set of semi-standard tableaux of shape alpha or beta with content gamma pi, whose word is anti-lattice word. For example, under this setting, we consider this tableau. This tableau is error tableau corresponding to these partitions because the shape is obtained from the partition alpha by removing the partition beta, and the content gamma pi, that is the number of letter 1 is 1, and the number of letter 2 is 2, and the number of letter 3 is 2. Also, the corresponding word is given by 1, 2, 3, 2, 3. Then this word is anti-lattice word. That is, in this definition, the word when we read the word from right, then the number of letter I is always less than or equal to the number of letter I plus 1. Also, we also identify these error tableaux with the companion tableaux. Then the companion tableaux are determined by the same rule as in the usual error tableaux. Then error under bar alpha, beta, gamma be the set of companion tableaux satisfying the rightmost entries in the ith rows is always less than or equal to n minus 2i plus 1. We call this error tableau flagged error tableau for Jn and SPN. For example, consider these companion tableaux in the previous example. This companion tableau satisfies this condition. That is, in this example, sigma 1 is 4, sigma 2 is 3, sigma 3 is 1. Then we can see that sigma 1 plus 2, sigma I plus 2i always less than or equal to n plus 1. So this tableau satisfies this condition. Now let me introduce the Lecouvey-Lenart formula. Let C under bar alpha, beta, gamma be the number of flagged error tableaux for Jn and SPN. Then Lecouvey and Lenart proved that for arbitrary lambda and mu, the branch multiplicity is also described as in terms of the subsection free sum in terms of the flagged error tableaux. We note that this formula also recovers the Littlewood formula without a difficulty. The proof of the Lecouvey-Lenart formula is based on a combinatorial model for the crystal graph of the integrable height-weight electron modules over the classical Lie algebra for type BCD, so-called spin model, which is introduced by Kwon. The flag error tableaux for Jn and SPN are obviously different from the Sundaram's error tableaux. An explicit bijection between these two error tableaux is not known yet, but a conjectural bijection is given by Lecouvey and Lenart. Both formula have flag conditions on the companions of error tableaux as the following. In fact, this observation is a motivation for our work. Then our main question is obvious. That is, our main question is that can we find a set of companion tableaux with a flag condition such that the branch multiplicity can be described as the subsection free sum in terms of these companion tableaux with flag condition for arbitrary lambda. To answer the question, we introduce flagged error tableaux for GLN and ON. For simplicity, we assume that n-2, 1 prime is non-negative. The result for other case is almost identical. Let it be a companion tableau. As in the symplectic case, we also consider the entries in the rightmost column of T, which denoted by sigma I. In orthogonal case, we need to consider some additional sequences obtained from the rightmost column of T. Then mi be the minimum of m minus sigma I plus 1 and 2i minus 1. Then nj is defined by the j smallest number in this set, depending on the index j and the sequence mi. Then the flag error tableaux for GLN and ON are defined by the companion tableaux satisfying the second rightmost entries in the J's law is always less than or equal to n minus nj plus 1. We denote by the error underbar alpha beta gamma with the set of these flagged error tableaux for GLN and ON. Let me give a simple example. Under this setting, we consider this error tableau. To verify this condition, we first consider the rightmost column. In this example, sigma 1 is 3, sigma 2 is 1. Then, by definition, m1 and m2 are given by 1 and 3. Then, from this, n1 and n2 are given by 2 and 4. Finally, the sum of nj plus tau j is always less than or equal to n plus 1. So this tableau satisfies this flag condition. Let me introduce our main result in this talk. Let's see underbar alpha, beta, gamma with the number of flagged error tableaux for GLN and ON. Then our main result is that for arbitrary lambda and mu, the branch multiplicity for GLN and ON can be described as the subsection free sum in terms of the flagged error tableaux correspond in terms of the flagged error tableaux for GLN and ON. We note that this formula also recovers the Littlewood formulas. Here, let me explain the main ingredients in the proof. In general, the branching rule for non-Levi type is more difficult than the branching rule for Levi type. To overcome this difficulty, we use the Howe duality. That is, by using the Howe duality on a Fock space for the dual pair T infinite and ON, the branch multiplicity for GLN and ON is equal to the branch multiplicity for T infinite and A plus infinite. So we consider branching for T infinite and A plus infinite instead of for GLN and ON. here, the infinite A and A plus infinite means the Casimir algebra associated to these thinking diagram, respectively. To compute the branching multiplicity for the infinite and A plus infinite, we use the crystal-based theory. In particular, we use the spin model for crystal base of type D infinite. The advantage of use this model is that there is a nice description of highest weight vectors of type A plus infinite in terms of LR tableau. To obtain this description, we develop an algorithm on spin model, so-called separation. By using separation algorithm, each type A plus infinite highest weight element corresponds a pair of same standard tableaus, where one of them is error tableau. Consequently, this separation algorithm induces an embedding from the set of type A highest weight elements into a set of error tableaus. The most difficult and technical part in our proof is to describe the image of this injection. Also, in fact, the sequences in the definition of flagged error tableau are considered to describe the image of this embedding. Yep. Our separation algorithm consists of a non-trivial sequence of Schuchenberger-Chudetaki slidings. And as an application, following the idea of type C in the recent work, Lecouvey-Lenart, we obtain a new combinatorial formula for the Lustig-QA multiplicity of orthogonal type with highest weight mu and weight 0. That's it. Thank you for your attention.
Yeah, thank you. If you you can watch the reaction. Yes, so we have plenty of time for questions. So Eric, can you go ahead and do the Q&A session?
Yes, so there looks like there's one question from Martin Ruby. I'm not sure if I'm understanding the details correctly, but the question is, did you compare your tableau with the constructions that appear in Judith Jagenteufel's paper from DIPZAC 2019? Or are you aware of connections?
Okay. I also I know that I know her results, but sorry, I don't know the connection between her tableau construction and our tableau. Yeah. Sorry. Yeah. I don't know where. So sorry.
Okay. I'm not sure if I saw any other questions in the chat, but if people have questions, feel free to add them.